Okay, welcome everyone. Here we are today for the ICANX Youth Talks. Today we'll be having two great talks on metal nanomaterials from Dayne and Leo Scarabelli. So our first speaker today is Dayne from Northwestern University. I don't know the title of your talk, Dayne, but the floor is yours. Let me stop sharing and give you the floor.
Okay.
And feel free to take it away whenever you're ready. Go ahead, Dayne.
Okay. Sounds good. Looks like the screen share is loading.
Yep, we see it. Looks good.
See it now? Okay. Sounds
Yeah.
good. All right. So, welcome everybody. Thank you for signing in around the world to hear today's talk. I'm going to present a talk entitled Challenges and Opportunities for Dilute Plasmonic Alloys. And if you're unfamiliar with that as a concept, I'd be happy to explain it over the next 30 minutes or so. All right, so I'm a chemist and a chemical engineer at Northwestern University, and kind of my mission statement today is to convince you that chemistry has really built the modern world. Everything that you see and you use on a daily basis, to the food that you've had for breakfast or lunch or dinner, has in some way been touched by chemistry, particularly in the modern sense of industrialized manufacturing. A lot of chemistry comes from a plant like the one that I show on my screen, but this has really been built out of 100 years of dependence upon fossil fuels or petroleum, both for the energy sources that we use for the chemical processes, but also as precursor chemicals to make the materials and molecules in which we all so much depend upon. Somewhere between 20 to 25% of the global GDP is impacted by catalysts and small metal nanoparticles or metal oxide nanoparticles that go on and actually reduce some of the energy barriers associated with these transformations. About 16 to 20 trillion dollars annually, and this number actually might be higher in 2023. It goes on to be impacted by catalysts and this kind of sector that I'm talking about. And about 90% of post-consumer products have been impacted by catalysts somewhere along their life cycle. So that might be kind of in the precursors, the origins of the petrochemical materials that impact our daily lives, or somewhere else along the line. One of the issues is with this that we are in some ways kind of stuck in a petroleum spider web. Everything from the fertilizers that we use to grow our foods are dependent on processes like steam methane reforming to create hydrogen to react with nitrogen to create ammonia. And ammonia is a basis for a lot of fertilizers around the planet. Also, things like plastics and monomer production from cracking of longer chain hydrocarbons to make things like containers that help keep food safe for longer, things like that. There's also a major dependence on the fossil fuel industry for things like pharmaceuticals and making small molecules that keep us all healthy. And even though we're talking today across the internet around the world, global transportation is something that impacts all of our daily lives in many ways as well. So this has been, over the last 100 years or so, an intricate network of advances. But the primary challenge with this is that despite the fact that we all rely upon it, we really need to push towards decarbonization and electrification of chemical manufacturing in the future. One possible way we could do this is to utilize light, and that's going to be a theme for what I talk to you about today, is the development of metal nanoparticles that can use radiant electromagnetic energy in the visible part of the spectrum to be able to drive these processes forward. So my lab at Northwestern is relatively new. We started up in January of 2022. So we're just about 2 years into the process of building a lab from scratch and really trying to make an impact in these global type of problems. Today, I'm going to share two aspects of what my research group does. The development of dilute plasmonic alloys. These are plasmonic nanomaterials that have strong electronic oscillations, but we dope in small amounts of metal to create active sites that are well-defined and controlled for the manipulation of small molecules, either in the gas or the liquid phase. I'll also have a couple of slides towards the end of today's talk and a bit more of a description about operando microspectroscopies. So these would be in situ techniques that we actually look at nanoparticles as they're behaving under real world conditions, either with gas flow, heat, or illumination all at the same time. And the reason that we're interested in that is because nanoparticles, particularly metal nanoparticles, are not static systems. A metal nanoparticle doesn't get locked in place and then stay that way forever. Environmental conditions can actually make this change in real time. And so we're really trying to develop techniques that allow us to get insights into some of these processes. My lab has two other areas that we've been really excited about over the last couple of years, and this is the development of photocatalytic metasurfaces. These are well-defined periodic arrays of planar surfaces, either of metal or dielectric. And we're interested in this because they're really great model photocatalysts that have tunable electric and magnetic fields that can be enhanced overall. We're also interested in non-equilibrium chemistries, and this is kind of a something that gets teased out of the plasmonic chemistry I'll tell you today, but I think there's a lot of other relevant systems to trying to understand some of these electronic effects in chemistry, vibrational effects in chemistry, and I think that that's going to be a big, big part of what we see as a part of the transformation of the chemical and energy industries over the next several years. All right, so jumping in, I told you about dilute plasmonic alloys. This is what a localized surface plasmon resonance is, or throughout the talk, I'll just call it a plasmon. So here we have a video of a gold nanoparticle isolated in space, and we have this green wave kind of flowing by. Light is an electromagnetic phenomenon or electromagnetic wave, and so it contains an electric and magnetic field that are perpendicular to each other. And when the electric field pushes on the electron density in certain types of metal nanoparticles, typically gold, silver, copper, aluminum has also been looked at. Doped semiconductors have gained a lot of precedence in recent years, but it pushes on the electrons and it creates this restoring force that causes this oscillation to happen. Now, as an experimental physical chemist, what we would actually see in the lab is that there would be a wavelength-dependent optical response that we would say is part of the extinction spectrum. The extinction spectrum is a combination of a scattering type of phenomenon where light can come in, create an oscillation of the electromagnetic field, and then light of the same frequency or different frequencies can be sent out. This is the basis for fundamental techniques like surface-enhanced Raman spectroscopy that can be used to detect molecules on the surface of metal nanoparticles down to the single molecule limit. There's also the opportunity when light gets shined onto these metal nanoparticles and induces a plasmon to have a resonance feature that ends up with the absorption of some of the energy that's contained within the photonic wave packet. And this, if not utilized, will actually end up in heating up these nanoparticle systems. This has been used by research groups around the world for photothermal heating, for drug delivery, and even as a therapeutic against certain types of cancer. Now, plasmons really have the opportunities for delivering some very, very unique chemistry. At time zero, let's see if I can get my clicker here or my mouse. Not sure if you could see that, but we have a time equals zero. We have this collective oscillation of the electron density, and by means of that, the electrons will actually absorb photonic energy from an area that's much, much larger than their physical size. And so plasmonic nanoparticles can be thought of as a nanoscale optical antenna. Now, within very short time periods after that initial absorption event of photonic energy, we undergo a process called Landau damping, which is going to create a non-thermal distribution of electronic energy much, much higher than what the Fermi level of the metal composite of the system that you're actually looking at is. And so these electrons and these holes that are now out of equilibrium with the rest of the atomic lattice, they can be utilized in some really interesting and effective ways that I'll say a little bit about today, but maybe we can get into more discussions in the panel at the end of today's session. Now, finally, if you have carriers that go up, they must come down, right? The same way that an apple will fall from a tree, the electrons and the holes and the lattice, they want to find themselves in equilibrium with each other, but over very short time periods, they're not. And so we have electron scattering, electron phonon scattering, electron surface scattering that all goes in to impact these different carrier relaxation processes. And so what my lab and many others around the world are doing right now is trying to take advantage of carrier relaxation and tune those pathways so that we could steer them towards selective photochemistries that utilize the carriers generated in plasmonic systems as kind of the primary tool of interest. Now, of course, if we don't capture those electrons or the electronic energy from a plasmon resonance, over time, they will thermalize and they'll equilibrate with the rest of the system or the rest of the universe in which they are confined. Now, there's a few interesting things about hot carrier generation, particularly in small metal nanoparticles, that I wanted to point out. And the next couple of slides are all kind of recent works by Thomas Rossi at Chalmers University. And these are time density or time-dependent density functional theory calculations that him and his group have been doing, which I think just kind of opens Pandora's box in some ways to kind of the promise and the exciting realm in which metal nanoparticle development from an experimental sense it might have in kind of really understanding the physics and the chemistry of these excited state non-equilibrium systems. So in this paper from 2020, published in ACS Nano, they used TD-DFT for the generation of a plasmon resonance in a small silver nanocluster. And what this group was able to show is that hot carrier generation and localization actually prefers to occur on places of under-coordinated sites within the nanoparticle itself. So based on computational restrictions, this is only a 561 atom cluster, so that would translate to a 2 to 3 nanometer particle. But what they see is that the electrons in these systems are actually going to localize at the corners. So you can see these areas of high electron density. So electrons with greater than 1 eV of energy, they localize at the corners. You can see some electron localization towards the edges. And these are, of course, on very, very fast timescales. But what this tells us is that when we think about heterogeneous catalysis and we think about nanoscience, really one of the main drivers of chemical reactions on nanoparticle surfaces are under-coordinated sites in the first place. So now we kind of have a confluence of effects. We have under-coordination of small nanoparticles, which is known to bind molecules very strongly and change energetics of particular chemical pathways. But we also have, under illumination, this generation of electronic carriers that have energies that are greater than 1 eV. That means that if a molecule sticks to the surface, has a reduced activation barrier because of that binding event, we can now utilize those hot carriers or those electrons to drive chemical processes with a little bit more ease. Rossi and coworkers also demonstrated in a follow-up paper published in Nanoletters in 2022 that the location of, let's say, a binding molecule is going to depend and dictate the energy transfer that can take place. Now, I'm summarizing a lot in this paper here, but essentially, the photonic density of states consists of a particularly strong peak when you have a molecule with a molecular orbital that will overlap with the frequency of a plasmon resonance. So if we can tune the optical features of a metal nanoparticle by a plasmon resonance, that's the collective electronic oscillation that I showed a video of before, and we can have a photonic density of states that overlaps with these two features, we can essentially get on-resonance effects, which can enhance the overall energy exchange of the electrons, the hot electrons I was telling you about before, into molecules of interest. And so that's another way we could think about hot carrier generation and how material effects are going to begin to matter through hybridization. Now, finally, in a third and final follow-up paper published in the Journal of Physical Chemistry C, again by Thomas Rossi and his coworkers in 2023, what they showed is that dopants in metal nanoparticles can localize charge. So plasmonic particles, copper, silver, and gold, have been studied quite a bit. And there's been a lot of work, and maybe Leo will tell us a little bit more about this later, is that if you could put, a platinum shell or a silver shell, and you can make these kind of complicated nanostructured geometries with a lot of metal nanoparticles, but we don't necessarily have to have a shell or a large layer. You could actually put in a single atomic dopant into the nanoparticle itself, and that will change the projection of hot carriers, again, the electrons in the holes, that may localize in those defect sites on a surface. Now, this is really interesting from the standpoint of the plasmonics and the nanophotonics community, but this is also something that's not unknown in the other side of the field in heterogeneous catalysis. So this is a large area of research for many, many groups around the world, because as you dope in small amounts of dopant metals, so reactive dopants could be something from the iron group, iron, cobalt, or nickel, or the platinum group, ruthenium, rhodium, palladium, osmium, iridium, platinum, so on and so forth, with these selective host metals, copper, silver, and gold, which happen to be the plasmonic metals that we think about quite a bit. As you dope these in, you can do something called break a linear scaling relationship. So typically in surface science and catalysis, there's linear scaling relationships with the association of absorption of molecules onto a particular type of material. And this has to do with the filling of the D-band structure. But by breaking the symmetry and putting, let's say, nickel into gold or platinum into silver, what we can do is we can escape these Bronsted-Evanston-Polanyi relationships, the BEP linear scaling relationships, and get activation energies that are no longer similar to the reaction energy that we expect from that linear law that's been dominating heterogeneous catalysis for the last 50 years or so. So we can lower individual barriers by creating active sites of platinum in a gold surface where that reaction typically wouldn't take place. Now, there's a lot of work that's in this space, and I have to say, and it's a really large area of modern science in terms of catalytic chemistry. And so, a couple examples here. This one is from Hannigan and Charlie Sykes, published in Science in 2021. This paper used both computational chemistry and experimental results to show that if you look at methane activation, so methane is the second most abundant greenhouse gas in the atmosphere, with a greenhouse global warming potential about 80 times that of CO2, right? So it's a very important molecule to be thinking about. It's also something that we have a ton of available through, let's say, natural gas formation, or even in like biodigesters and things like that. So if you look at methane activation on a copper surface, you can look at the orbital hybridization here and see that there's not really much activation in the system overall. If you put the same molecule on platinum, you see that there's a much stronger overlap between the frontier orbitals of the platinum system and the incoming methane molecule. But if you mix these two together and you have, let's say, rhodium in copper, now you get much stronger hybridization in the system overall. And we could look at kind of the landscape potential diagram that's calculated here for the breaking of individual CH bonds. We see that in the case of platinum, if you follow the blue line on the screen, we end up with a negative energy, which means that the absorption of methane and that central carbon atom is going to be very strong, and it's going to lead to something called coke formation. It's essentially amorphous carbon that gunks up your nanoparticle surface when it's all said and done. However, if we look at copper as just an individual coinage metal, we see that there's a really high potential barrier to be able to activate the CH bond in methane. But by doping in a small amount of rhodium at the single atom level, we see that we get some Goldilocks zone. We can actually do this chemistry with very little of the precious metal of rhodium, but much reduced energy penalties, and in a regime where it's a little bit uphill, so we don't get coking, but not all the way uphill as well. There's also a realization by others in the community, this work comes out of the lab of Cynthia Friend at Harvard, that we don't necessarily need individual atoms to make this chemistry take place. We could actually have a small amount of dopant. In this case, they synthesized gold palladium nanoparticles, and they looked at the regime where you have individual single palladium atom dopants, but then also small clusters or rafts of palladium inside the structure. And they showed that depending on how much palladium you have, and whether you have single atoms or dilute rafts, that you can get a dissociation limited regime or a recombination limited regime for the hydrogen dissociation reaction. So again, it's a model system, but it shows and demonstrates, and I think there's been some other work as well recently that shows that you don't necessarily have single atoms to really push this forward. And that's why the field that I'm pursuing in my lab is this area of dilute plasmonic alloys, not necessarily at the single atom limit, but in the regime where we can control active sites and surface chemistry, but not completely damp out that plasmon resonance that's so important. So there's been a couple papers published in this field so far, and I want to give credit to Professor Linan Zhao, who is my colleague in my PhD at Rice University, who's now an assistant professor at South China University of Technology. Linan, in his PhD, was developing these copper ruthenium nanoparticles and demonstrated that they have some supreme efficiency for a dry methane reforming reaction. But only when you have the ruthenium atoms diluted down to the single atom regime do you get the level of reactivity and long-term stability that would be expected from a catalyst that could actually go into some commercial applications and go on and make an impact in the real world. If you have pure copper, you can drive dry methane reforming, but the absorption of carbon to the copper itself is actually going to be limited for coke formation. So you get high CH mobility, and those CH molecules can bind together and gunk up the surface, and then no more carbon dioxide or methane can go in and activate. If you have too much ruthenium, you actually anchor the carbon to the ruthenium itself. But if you can have a regime where those individual ruthenium atoms are dilute and spread out in that system, you can get long-term photocatalytic stability and selectivity, as shown in this plot in the middle. Lee and I also worked on a project where we looked at ammonia decomposition in these copper ruthenium catalysts. So this was about 5 to 10 weight percent, which was in a regime where we likely had some single atoms, but probably had some rafts at the same time. And what we saw is that we have a wavelength dependent effect, which is really important from the fundamental physical standpoint of this, is that on resonance with the copper nanoparticles and at the highest light intensities, because these are nonlinear processes, we see that we can have a reduction in the activation barrier, from about 1.2 eV all the way down to 0.3 eV. So 1 electron volt change in the apparent activation barrier of the decomposition of ammonia, because we're on resonance with the plasmon and the hot carriers are contributing to the desorption of nitrogen atoms from the surface. It's essentially a self-cleaning nanoparticle surface that can be driven specifically with light. Another important feature that was reported in the science paper in 2018 was that the rate dependence based on the partial pressure of ammonia will actually change whether you have this metal nanoparticle illuminated or the metal nanoparticle heated up, right? So heated up would be the traditional way that the chemical industry has been operating these systems for 100 years. We see a 0th order dependence, which means it really doesn't matter how much ammonia is in your system. You basically have a rate that is constant. But by having light introduced to the system, we change the reaction order to pseudo first order, which means that for every molecule of ammonia that comes in, we have a rate that's associated with that change of the total concentration, which means that we could actually engineer these systems using light to have a completely different response than if we would just do it the same old, same old. So photonic energy can really, really make a big difference. I want to put up a slide here next, just kind of acknowledging that there's a long history of single atom catalysis, and now there's an emerging area of dual atom catalysis where you actually get synergistic effects between two dopants all the way down here at the end in 2023. There's an example of platinum and chromium for ethanol dehydrogenation. So ethanol, which can be abundantly formed through, let's say, the reforming of grain or something else, you can remove hydrogen from that system selectively, make acetaldehyde, which is, again, a value-added chemical precursor, and generate hydrogen all at the same time. So there could be opportunities here looking at a silver nanoparticle, so this is all done kind of surface science approach on extended single crystals. But if you had a silver nanoparticle with a plasmon resonance and you could dope in platinum and chromium and use ethanol from a bio-derived source, there could be opportunities for hydrogen generation while at the same time generating some precursors or some output products that have some value that aren't all the way down to the kinetically and thermodynamically favored process of CO2. So there could be a lot of interesting areas in that. For everybody's reference that's online today, if you're interested in this area, there's a ton, or 12 references here that kind of follow the history of this field. There's a lot of other papers in this space as well, but I think this is a really interesting area to consider moving forward as we think about metal nanoparticle design and its opportunity in catalysis. So some of the work that's going on in my lab to kind of address these things are basic synthesis of gold platinum alloys. We use a very classic approach that both Matt and Leo know quite a bit more about than I do. But we're taking hydrochloric acid and citrate. We're doing a temperature reduction, so basically just reducing these in aqueous conditions. We get about 15 nanometer gold spheres or pseudospheres. They have a relatively strong plasmon resonance at about 525, 532 nanometers, and this is that kind of the experimental spectrum that we've collected. And then what we do is we inject H2PtCl6 and ascorbic acid to do another reduction, kind of a stepwise reduction. And it takes our initial 15 nanometer seeds, coats them with some amount of platinum. We can vary this anywhere between 0.5% up to 10% and still get these dilute regimes available. And what you see here is that you get a broadening of the plasmon resonance and a slight damping, but you still maintain some of those strong absorption features overall. Now, these nanoparticles, what we do with them to make them actually catalytically active is we do electrostatic adsorption of the particles that are capped with citrate onto the surface of gamma aluminum oxide. Gamma aluminum oxide in this case is just representing an inert host material that's going to basically support these particles, stop them from aggregating with each other, and be able to maintain the individual resonances that we are interested in. So some TEMs of the supported nanoparticle system, we can vary the weight loading pretty easy by just changing the amount of nanoparticles and concentration of gamma aluminum oxide that gets injected. And then we do techniques like X-ray photoelectron spectroscopy or XPS to verify that we have both the concentrations and the of gold and platinum within the system. In my lab, we're also interested in a few other synthetic techniques, and since today's talk was about metal nanoparticles, I figured I would share these and just kind of introduce them. The first one is being the development of synthetic minerals, primarily copper-based hydrocalcites. These are precursors in generalized ways to form these dilute plasmonic alloys. So the hydrocalcite supergroup structure kind of looks like this, and I won't go into kind of the details on this, but what you do is you actually create a layered double hydroxide of the support atoms, so magnesium and aluminum, and then you can actually inject the metal precursors that you're interested in. In this case, we use copper, but any other kind of 3-oxidation state cation, metal cation that gets put into the system creates these layered structures that we can then go on to reduce under a hydrogen atmosphere after calcining, and we remove the copper from the overall layered double hydroxide structure, reduce that down, and then we've got these metal nanoparticles that sit on the surface. So here's a couple examples. This is a really exciting type of synthesis that we use because it allows us to kind of vary the support material while at the same time varying the nanoparticle size and distribution overall. Finally, another technique that we use quite a bit in my lab is strong electrostatic absorption. This is great because it gives desired catalyst properties such as small, well-dispersed particles, allows for easy alloying, and allows for great light absorbance, which of course is what we're going to want in a photocatalytic system. So here what we see is that most metal oxides are amphoteric. They're going to have a hydroxide group that's sitting on the surface, and we can adjust the pH of the overall solution to either protonate those or deprotonate those. And so we work in a deprotonated kind of regime. So we have negative charges across the surface of our oxide. And then what we do is we introduce metal cations in low concentrations. And so they will get absorption of mixed metals onto the surface of whatever support we're interested in. Here, we're just showing silicon dioxide. This is so a copper 2+ and a nickel 2+. We reduce those in hydrogen with a little bit of heat, and you will actually aggregate to make these small nanoparticles. So this is just a TEM image of kind of what those catalysts would look like. You can see that we have really nice dispersion of small particles across the surface, and we have some mixed metal states. So in this case, we're making copper platinum that's dispersed onto the surface of SiO2, which we can then go on and use tools like X-ray photoelectron spectroscopy to confirm the presence of both copper and platinum in the system. And of course, there's many, many other characterization tools that will be needed to really understand the local bonding environments and the dynamics of these systems overall. So I introduced in the beginning opportunities for understanding photochemistry and photocatalysis, specifically for displacing some of the legacy technologies of the chemical industry with things that could be electrified like light. And so our system that we use in my lab kind of looks like this. This is actually 2 8-by-8-foot laser tables that are backed up together in the shape of an L. And so just kind of an overview of some of the research that we do in my lab. We've got a super continuum laser down at the bottom of the screen, bottom right. We have a series of gas flow controllers that direct to one or another different reactors. And in those reactors, what we can do is diffuse reflectance infrared spectroscopy, or DRIFTs. This allows us to use illumination and infrared spectroscopy at the same time to determine how light changes the vibrational features of molecules on the surface. We could also do use a flat top reactor and do operando Raman spectroscopy to determine how, again, in a similar way, we're looking at the vibrational structure of molecules on the surface. We also use mass spectrometry and gas chromatography to analyze what the reaction outputs are going to be at the end of the day, so we can look at large-scale chemical reactions and mix and match different materials, flow conditions, heating rates, so on and so forth, to try to understand these things. Okay, so a couple of preliminary results that I'd like to share today would be looking at operando carbon monoxide drifts, because this can reveal catalyst surface restructuring in real time. So in this case, we're looking at a gold platinum catalyst that we made through colloidal synthesis. And what we can see on the leftmost plot is looking at 5 minutes post-exposure to carbon monoxide versus the original kind of flow conditions of the carbon monoxide itself. So here what we see is we get a narrowing of the vibrational features, which are actually indicative of the carbon monoxide binding to the platinum atoms that are stuck on the surface. And depending on the concentration of those platinum atoms and whether they're right next to each other and we have a bridging carbon monoxide, or we just have an end-on carbon monoxide, this technique is going to allow us to kind of see and understand that. And so some of the results that we've seen most recently is that if we look at 15 minutes post-exposure, we get this narrowing of these resonance features, which is actually indicative of actually having these platinum atoms, which might have been clumped up together upon initial synthesis, actually spread out across the surface of the gold and get more localized and isolated overall in those systems. We can also look at, so I mentioned CO as a probe for drift studies. We're also able to introduce things like hydrogen gas into the reactor at the same time to look at the formation of hydrogenated products and higher order products as a function of light on, light off. So here, I'm not going to go too much into this this work right now, but wherever you see these yellow bands, that's actually a laser illumination being put into the system. And this is a real-time mass spectrometry trace of the reaction products that are coming out. We can heat these up and look at the synergies between heat and light at the same time. And this is a tool that we're really using to push forward and understand these systems a little bit better. So kind of on this, I wanted to say that there's a lot of opportunities for theory, surface science, and catalysis to loop in all together for rational catalyst design. And there have been a lot of opportunities and examples of using theory-guided catalyst design to really understand what we're going to want to do in terms of a chemical reaction before we go in the lab and make 100 different types of metal nanoparticles and try to shape and understand these. And so a couple of these where theory was used to predict catalyst design are nickel gold for steam reforming, rhodium copper for propane dehydrogenation, and again, the one that I had mentioned before, the platinum chromium on silver for ethanol to ethanol dehydrogenation, which again could be really useful for, let's say, the generation of clean hydrogen from a bio-derived source. All right, so a lot of opportunities here. And then I think because we have a couple more minutes, I'll just give a few more slides kind of about another technique that we're developing in the lab and something that's really kind of important for what I work on. And this is using the electron microscope as a tool for understanding plasmonics and photonics. And so the typical electron microscope looks something like this, although it's very, very simplified to what you may actually see in your lab. And particularly in the realm of looking at plasmonic nanomaterials, there's a lot of techniques that already exist within the electron microscope that could be applied and understood a little bit better. So the first one is electron energy loss spectroscopy. This is looking at the energy that the electrons lose as they move through a material system. Cathodoluminescence, which is the emission of light off of a nanoparticle that might exist within your electron microscope. And then more recently, there's been a lot of opportunities for using specialized holders to actually see in situ chemistry. And so you can introduce gases, or you can introduce light, or you can introduce liquids into the electron microscope now and really be able to understand all of these different aspects that nanosystems, nanoscale systems are going to be able to undergo really with atomic resolution and a lot of time resolution as well. And so speaking of time resolution, the tool that I'm going to be talking about today is the ultra-fast electron microscope that's housed in the Center for Nanoscale Materials at Argonne National Labs. And so rather than a holder, we actually have a ultra-fast laser that's coupled into the electron microscope, where we will kind of use a beam splitter and a third harmonic generation to create a 258 nanometer probe pulse. This creates a stroboscopic electron wave packet that images our sample. And we use a second harmonic generation 515 pump beam that would excite the plasmon resonance of the nanoparticles that we're looking at. The technique that I'm going to present on today is something called photon-induced near-field electron microscopy. And so given the time, I'm not going to go too much into this, but what this technique does is it looks at the electrons as they move past a nanoparticle or some nanoscale object, and it looks at the charges that redistribute. And then what we see is that those passing electrons are either going to go through stimulated absorption or emission as they pass through. And so what this does, it gives us a zero loss peak. This is the central peak of zero energy loss. These are the electrons that pass right by the material and don't exchange energy. But what we do get are these symmetric side bands that exist in these spectra from either the gain or the loss overall. So the sideband population is therefore just the integral along the electron trajectory. But compared to the traditional techniques that have been used in nanophotonics over the last several years, EELS, cathodoluminescence, INM is extremely efficient in terms of how much energy is exchanged between the electrons and the photons that are being scattered off of the surface of your nanoparticle. But it also allows for nanometer scaled spatial resolution, field mapping, femtosecond, or even attosecond. I won't talk about that today, time resolution, and milli-electron volt spectral resolution to see how all these energy exchange processes are taking place. And I think this could be a really important area of development over the next several years. So the system that we're using, a little bit different than what I had shared in the first part of the talk. We're looking at aluminum nanocrystals as another plasmonic entity. But what we do is we wrap these particles with silicon dioxide. And this is actually performed by my colleague, Ben Clark, who's now at a company in the United States actually doing nanoparticle synthesis for his job. So couple early results from this work is looking at PyNem field maps of the aluminum nanocrystals that are wrapped in the silicon dioxide. What we can do here is you have your regular TEM image of the individual particle, and then you see the field plots. So these are the dipolar plasmon resonances. If you think back to the video that I showed before with the electronic or the oscillating blue wave, this is essentially the experimental result showing those waves in real time. And the arrow, as it rotates, is actually the polarization of the pump beam. So we can see that we have a polarization-dependent response to the optical properties of these nanomaterials, as well as the typical asymmetric PyNem spectrum with the sideband showing the energy exchange in these systems. We can do laser pump fluence, and we see that as we increase the energy, we get stronger field enhancements overall in these systems. And this, again, it kind of gives us some insight into how metal nanoparticles, particularly plasmonic metal nanoparticles, are behaving both in terms of field strength and intensity overall. So with that, I'm going to conclude by saying that I really believe that dilute plasmonic nanoparticles are really an underexplored platform where I think there could be a lot of work in the future, particularly this kind of integration of light to look at the role and localization of hot carriers. There have been some initial computational studies, but from an experimental aspect, I think we still have a lot to learn. And that finally, operando, in situ, microscopy and spectroscopy are going to enable in the future insights into reactivity and structure of how all these materials and nanoparticles interacting with each other. So I'd like to thank my team, everybody who's working with me on these various different projects, as well as the funding agencies, and of course the invitation to speak today. I'm looking forward to the panel discussion at the end. Thank you.
All right, thank you, Dayne. That was fantastic. Obviously, we'll wait for the discussion to have questions and further discussion. Leo, are you ready to go?
Yes. Let me share my screen. Is this you guys seeing it?
That looks great. The floor is yours, Leo. Take it away.
All right. Let's go presentation mode. And okay. So hello everyone. Thank you very much for joining in, and thanks Matt for the invitation. I'm really happy to be here and share our work on plasmonic metamaterials, and also thanks to Dayne for introducing a lot of the things that I taking care of, but the best part of my introduction, so that makes my job a little bit easier. So we are currently locating at the Institute of Material Science of Barcelona, but actually my group will be moving very soon. So we are currently under this very tedious process of moving the entire lab elsewhere. But so as Dayne very well introduced the importances of and the impact that plasmonic nanoparticles had in pretty much any field of science in the last 10, 20 years, thanks to their localized surface plasmon resonances. He did a very good job at explaining how this worked, but there is an introduction, just to reiterate, there is an interaction between light and nanoparticles, thanks to their size and their electrons. They are capable of having this very strong interaction, which translates in very intense absorption, which can be used in several ways, both in the promotion of optical phenomena, but also has hot electron generations, and of course light to heat conversion, as was previously mentioned in the previous talk. So all these motivation lead to pretty much my life as a PhD student, which I summarized up here, where we basically took a very almost 3 decades now in looking at how we can control synthesis and chemistry in order to produce nanostructure that have different sizes and different shapes and different composition, which would impact their optical properties and their crystallography. So this is just a few examples from my thesis, and we can look at using advanced electron microscopic technique at their shape, their size, and how the plasmons will distribute and what kind of energy is associated with them. And it still amazed me how much work has been done and how far we've got recently, even in the synthesis of chiral shapes, and how well can we control not only the general shape and the size, but now we're very good, at least for some metals, to look at we kind of playing fields with kind of defects we can create, and as Dayne shows, even creating alloying that are diluted alloy, not only diluted alloy, but many other type of systems. However, from an optical perspective, there are some limitations, which are intrinsic to the system, which is related to the fact that these kind of nanoparticles present very big optical losses, which basically translated in these kind of resonances, which are pretty wide. And so we can express these optical losses. We are looking at the efficiency of basically the resonance. And so looking at the full width at half maximum over the energy, which is expressed as a quality factor. So to give you a ballpark, generally colloidal system don't go above 10 in terms of quality factor of their localized surface plasmon resonances. And so there has been a very huge push from the community to try to address this problem, try to access a higher quality factor structure. And so if we look at this from theoretical standpoint with a coupled dipole approximation theory, which basically means that we are treat our nanoparticle as a dipole, we can look at their localized plasmon resonances basically as the response to the electric field, which is modulated by the nanoparticle polarizability. So this is a case of an isolated nanoparticle, very simple. But what happens if we have more nanoparticles? So we not only have the interaction of our nanoparticle with the external electromagnetic field, but we also have an interaction with all the electromagnetic field of the other particles. So there is basically perturbation. So we can do a sum of all these perturbations for every single particle in the system, and we can simulate all this. And so what we see here, for example, in the case of two nanoparticles interacting with each other, is that this will strongly depend on the distance between the particles. And even we can simulate even more complicated cases, but the overall message is that we'll have two types of plasmonic coupling, one taking place when the nanoparticles are very close, which is called near-field coupling, so where the distance between the nanoparticle is much smaller than the wavelength of the light using to probe the system. And this is a very strong perturbation. And this is what is used to create the hotspot. So basically, the plasmon of each nanoparticle will interact with each other and will hybridize, pretty much very similarly to what a molecular orbital will do in a molecule. And so what happened is that we will create a very intense area between the nanoparticle where the generated electric field will be very intense. However, if we look at the problem that I presented at the beginning, so the fact that these systems have very high optical losses, this is actually a source of optical losses. So basically, as you can see in both graphs down here in these two plots, the plasmon associated with the dimer in this case, or with the tetramer in this other, are even broader than the one of the isolated particle. And then in the other case, we have the far field coupling, where the distance between the nanoparticle is much bigger than the wavelength of light, which is a very weak perturbation, and we generally consider this a negligible effect. So we treat particles that interact in the far field as basically isolated particles. However, the scenario changes if we place our nanoparticle in the periodic distribution. And what happened is that with the diffraction is added to the system, because this will behave basically as a grating. And we can also simplify a little bit the math, because we can basically assume that the perturbation tensor will also be periodic, since the distribution of our nanoparticle is periodic. And so to make quite a long story short, you basically get down to this equation, which is what is important here is that we observe that in order to have a resonance, so basically in order to bring this denominator to zero, we create new conditions that are not localized plasmon. These are new resonances, which will depend both on alpha, which is the polarizability of the single nanostructures, and G, which is the tensor. And we can assume that while alpha depends on the single unit, so it will depend on the size, it will depend on the shape and the composition of the nanoparticle. G, we said that I just said that is considered to be periodic, so it will depend on the geometry of our array. And so the effect is very well exemplified in this plot over here, where you can see that you have a much more intense resonance, which is much sharper. if we think about the Heisenberg principle, the much sharper resonance means also a much more long-lived resonance and also much more delocalized. So while localized resonances typically decay in the order of picosecond, for lattice plasmonic resonances, which are collective resonances of the entire array, these resonances can last up to even microseconds and be spread over a much wider surface. And this could be very interesting, for example, for catalysis, where normally we have a big mismatch between the generation of a hot carrier and the time scale that we typically have for chemical reactions. So we basically have a very short time frame where we can do these electron transfer that we talk about between the nanostructure and the molecule that we need to perform chemistry on. While if we would be able to use this lattice resonance, we would have much more time to do it. So the one way to explain, to understand this effect is that the decay will depend on the distance. But if I go to one distance away from our nanoparticle, I add d to the square dipole to the system. Okay, so basically my resonances is reinforced, and therefore it becomes much sharper. So basically, what I want you to take away as take-home messages here is that building plasmonic arrays is a very convenient way to overcome the optical losses of the system, maintaining the plasmonic properties and the absorption of these nanoparticles. So traditionally, these type of metamaterials and plasmonic metasurfaces have been fabricated using what we can call traditional nanofabrication techniques involving complex evaporation and electron beam lithography technique, which have proven to be extremely helpful in understanding this type of system and also in applying them in several fields. However, there is this metamaterial field is exploding every year more. There is both in terms of publication, but also in terms of market value. And there is a general trend that is becoming apparent in the community that the next step would be to create metamaterials that can also can be more dynamic and can chemically interact with the environment. And this is something that is very hard to do using traditional nanofabrication approaches, as they offer limited control to the crystallography of the system, to the type of metals and substrate that you can use, and as well, they are generally limited to, and they have very high resolution, but only in XY. It's much more complicated to build something in the Z direction with the same quality and properties. So a big push here. I will take a couple of examples from my own work and from my own lab, but I just want to mention that here there is probably like 100,000 of paper on the subject. And the idea is, okay, can we build this type of structure using colloidal nanosystem? Because as I mentioned in the beginning, colloidal nanochemistry offers the possibility to control extremely well not only the size but also the crystallography and the chemistry, the surface chemistry of the nanostructure composing the array. And so amongst many techniques available for doing this type of self-assembly, we picked templated colloidal self-assembly, where we simply take a colloidal solution and we let it dry under an elastomeric stamp that is then lifted off after drying. And so we can control, by modifying the geometry of the stamp, we can control the lattice geometry. And so how can we, let's see if this works in improving the quality factor. So here we have just a few SEM pictures of type of surface of arrays that we can produce in the lab using 50 nanometer nanoparticles. And as you can see here, we do observe a shift to the red. So here in this area, these are gold nanoparticles. So the localized plasmon would be centered around here, but then you will see some shift, but these are definitely not sharp. And here what you have, the dotted line that you see here is where the theory tells me that the lattice resonances should be. And so you easily realize that actually the major peak that you observe here are not the lattice resonances, but are still delocalized. And this is because you have to keep in mind that these are clusters. So therefore, there will be near field coupling in here. Basically, this system is extremely more complicated because you will have both near field coupling and far field coupling mediated by the array. And so this is just to explain the importance of doing a complete characterization where we also change the illumination angle. And this will allow us, since the lattice resonance will also depend on the illumination angle, we will be able to move the lattice resonance. And so you will actually observe that, for example, in this case, at 37, almost 40 degrees illumination angle, the expected lattice resonance, which is this white line over here, should cross my localized resonance and appear over here. And that's exactly what we see. But once again, problem is that these lattice resonances are definitely not sharp, which means that we still have a very big amount of optical losses in the system. And so we started thinking, how can we improve this? And so we looked into using different size colloidal nanoparticle to reduce optical losses. And what we observe is that, of course, if we increase the size of the particle, we observe a much sharper resonances. And this is due to the fact that we will start having single nanoparticle array. But this is very, very complicated to do. The array are not very uniform due to the fact that, placing single nanoparticle using a colloidal templated subassembly system is not easy, especially over a vast area. And so, but what we observe is that even if we reduce the size of the nanoparticle, we started to observe something extremely sharp. And this was interesting to us, and we tried to understand the system. And Nicholas ran some simulations, and it turns out that what is going on is that by reducing the size of the nanoparticle, we pretty much reduce the amount of near-field coupling that we have within the cluster, even though we increase the amount of nanoparticle composing the cluster, so the repeating unit. And this is due to the fact that the interparticle distance compared to the size of the particle will increase. And so in the middle case scenario, where we have around 50 nanometer nanoparticle, you will have an optical response that is dominated by the localized surface plasmon resonance of the cluster, and so to the near field coupling. While if we move either to single nanoparticle array or small nanoparticle array, we have we can compensate these optical losses thanks to the far field coupling, sustaining our resonances over the entire array. And so moving towards sharp lattice plasmon resonances. So basically, by optimizing and implementing what we learned, we were basically able to show over 60 quality factors over 60 for this type of system. As you can see here, this is the most the optimized case. And this basically gives us the first example of basically told us that we can prepare high quality factor, we can obtain high quality factor resonances using colloidal system. And so in the next example, I show you one way that we could use those high quality factor lattice resonances. And this is work done by Ili. She's currently a PhD student in my group. She will most likely graduate early next year. So in this case, what we did is that we performed a very similar strategy that you've seen in the previous work, where we drop casted a nanoparticle solution and dry it under a mold. But in this case, before performing the self-assembly, we spin coated a photoresist layer containing a dye. And so what happened here is that, as you can see, once again, we are looking at centimeter scale self-assembly. The SEM are really, really nice. And what we observe is that in this case, we have, again, even sharper lattice resonances, again, where the position of the lattice resonances will depend on the geometry of the array. So we can have a 400, 500, or 600 array, the spacing between each cluster, and then we will observe my lattice resonance at around 630, 750, and 900 nanometer, more or less. And so the dye that we chose was rhodamine beam, and the reason why we chose rhodamine beam is because the emission will overlap quite well with the L400 case. And the idea was to use this very sharp lattice resonance as an optical cavity, which should promote lasing. So what you see here in the slide, this is a K-plot of the system. And so we have a high concentration of states right here in the normal direction. So what we should observe is that by illuminating with our pump the structure directly from the top, we should observe a lasing emission coming out at normal direction. And this is what the theory predicts. And this is pretty much what we observe. We have a very, very good overlap between the theory and the experimental data. And so what you see here in gray is the emission of the rhodamine B outside the below threshold, so on top of our particle but below threshold. And here in red, you see how the emission of the layer changes above threshold, so it becomes much sharper and much more intense. And so in order to confirm that this was a lasing emission, we also performed a divergence and a polarization study, confirming what we predicted by theory. And so even more interesting is that by changing the lattice parameter, so going, for example, to 500 nanometer, in this case, we do not expected the lasing emission to come out straight out at normal incidence, but actually we expect it at a slight angle. So these dotted lines here are 10 degrees separation. So we expected these to happen close to 20 degrees. And once again, this is what we observe here. So that at plus 17 and minus 15, that we do observe this sharpening and intensity increase in the emission of the random beam. So once again, the typical threshold plot for a lasing emission and the divergence angle. Okay. So in just a conclusion of this self-assembly is that I wanted to show you how colloidal self-assembly are not only versatile technique to build this type of system, but we are actually getting to the point where we can access very narrow lattice resonances, which can be used to promote nonlinear optical phenomena, which is something that has been proven, but in very few cases. But I think that now we are getting more and more competitive compared to standard nanofabrication approaches. And one of the main advantages of our cavities is that we have an open cavity. We have an open system where then nanostructures are actually built on top, and we can access the surface chemistry of our nanostructure. So we would be able to exploit this nonlinear effect, for example, for in the case of strong coupling systems or more advanced nonlinear optical effect. In a way that would not be possible using standard nanofabrication approaches. However, this is all very nice. I mean, colloidal self-assembly, we can do all this beautiful structure, but we also have to realize that when I show you the fabrication strategy, I also omitted a few steps. So typically, what we do is that we have to do a colloidal system that it's several liters. And then we need to purify the system, we need to concentrate the nanostructure, and we need to perform a ligand exchange. And then only then we can perform a self-assembly. And also these type of self-assembly typically are very, very much related on delicate conditions that are unique for every system. And so every time I change the colloidal suspension characteristic, I need to basically go through a re-optimization step. And so these are very major drawback, and the 3D organization of nanocrystals that are synthesized in solution remains, at least in my opinion, a major bottleneck in the preparation of this type of structure. And so we started thinking about a year ago, and how could we solve this issue? Is there a way? And what we kept coming back to was the idea of performing in situ growth, which is definitely not a new concept. Here, the idea is that, okay, we can take a substrate, we can functionalize it, we can attach some seeds, and then perform an in situ growth. And so there are a few examples in the literature over the year where this has been attempted more or less successfully. But as you can see here, compared to the TEM images that I showed you at the beginning of the talk, the quality of the prepared structures is typically much lower, both in terms of size control and shape control. And so this has prevented this area of research to really grow in the same way that we observed for colloidal synthesis. So we started thinking about this and think what was missing, what was the problem here. And so if the question is the problem that we identified is that it's very literally we talk about pattern in situ growth. So generally what you do is you control your nanostructure will form on the surface, but not where. And so since you do not control where, it's really hard to obtain an homogeneous product. And you lose a lot of control over the type of structure that you're growing. And so the idea is to finally reach this kind of stage where you start from raw materials and you create nanostructure that are fully functional and that also customizable. So I can think about a multi-step growth, the same way that we do in colloidal synthesis, but directly on the surface at specific location. And so the consequent benefit of this idea would be to not only control the morphological and crystallography control in situ, but also to control the pattern orientation. So how my nanoparticle is growing compared to the substrate, which is something quite challenging to do when you do a self-assembly approach, and also to have a much more intimate control over the substrate nanostructure interaction. And so the challenge is, if we ask them why nobody thought about this before, where I believe that everybody thought about this, but the challenges are how to regulate the nucleation density and how to control the chemical environment. And also, and finally, very importantly, how to suppress secondary nucleation, because this whole scheme works only if you can avoid that your nanoparticle will grow at the same time on the substrate and in solution. And so the idea that we proposed was to use chemical contrast in situ growth, where we use chemistry to modify the substrate. So we obtain a chemically patterned substrate that then the idea is to expose to a growth solution and then have only selective on-substrate nucleation at specific location with nanoscale precision in order to prepare our metamaterials. So in this case, Illy joined forces with Gail, a visiting student from UCLA that is now working in the lab of Professor Liz Marsan in San Sebastian, here in Spain. And so the idea is basically to have these chemically patterned substrate and then grow our nanoparticle on top. And the way we ended up doing this is to take a PDMS substrate or supported PDMS substrate, spin coat a layer of hydroxypropyl cellulose, and then perform nanoimprint thermal lithography. And then at this point, we will etch the residual and spin coat our chemical ink, remove the HPC, which is soluble in water, and then perform our growth. So this all looks very fine and easy, but it's all, of course, not as easy as it looks. So first of all, we need to prepare our cellulose stencil, the mask made by cellulose. So as I explained very quickly in the previous slides, we spin coat our HPC on top of the PDMS, and then we perform these pattern with this pattern using non-imprint lithography with that hard PDMS stamp. The very key aspect here is the PDMS. So why we use PDMS and not, for example, silicon? And the reason is that if you think about if some of you worked on non-imprint lithography, you generally cannot do very thin layer. And the reason is that you need the amount of material that you are deforming in order to make your nano imprint to be able to occupy the entire volume of the stamp. So if I try to do very, very thin layer, what happens is that my stencil will be very, very poor in quality and in fidelity reproduction of the pattern geometry. However, if we use a soft substrate, we observe that we could go down as we could make HPC stencil as thin as 30 nanometer. And the reason that we believe this is possible is that I think a soft substrate I could press into the substrate and basically force the HPC to fill the stamp evenly. And so another important benefit of this is that we would not have so much residual layer that we'll have to etch in the second step. So we only perform a 30-second UVO zone cleaning step, which is really making our life much easier, and we can avoid any kind of clean room steps. So everything is done benchtop, everything is done in a standard chemistry lab. So once we have our HPC film, as I mentioned before, we do this UVO zone cleaning, we spin coat our chemical ink, and then we remove the HPC stencil and we obtain these chemically patterned substrate that is ready for growth. And so once again, this was not as easy. The growth step, we struggle a lot with this because we always observe some secondary nucleation. So we took a bunch of time in optimizing our growth solution in order to avoid the secondary nucleation. We observed that the quality of the water is, of course, very, very important. And we also basically added some, in this case, some CTAB to retard, as you can see here, the nucleation of nanoparticle in solution. This is a simple reversible study where we observe the extinction of the solution to catch any nucleation. So we make sure that we don't observe any nucleation up to 10 minutes, and then we stop our growth around 5. And then finally, this is our first results that have since then improved quite a lot thanks to the work of Pau, which recently joined the lab. And so as you can see here, we're now getting to the point where we can have a large area growth of nanoparticle only a specific location directly in an array. So we prove the flexibility of our system by increasing changing the size, by varying the amount of the time of growth, and also by changing the shape. So by using basically our first grown nanostructures and then overgrown them into gold nanostars. And we are now moving on past this, and we're now looking into, creating core shell structures and so on and so forth. Basically, trying to integrate what we learned from colloidal synthesis down to into this kind of systems. Just a few points that I'd like to point out here. This is just basically an overview of some statistic that we perform on this type of system. But what I was really impressed about is that we observed that 90% of the particle grow within the pattern, so where the area is. And what I think is extremely important moving forward is that we observed that an average of 2 nanoparticles per region. And this is surprising to me at the beginning, since the area of, let's say, the grow active area that we prepare with our methodology is about 230 nanometer in size and diameter, and our nanoparticle is as low as 40 nanometer. So this means that once we have a nucleation event, there is a low probability to have a secondary nucleation event, as the growth of the already present nuclei is favored. And this is extremely important moving forward. Finally, though, I promised you that this was to do some plasmonic metamaterials. It was the whole purposes of this methodology. So, can we actually observe some metamaterials behavior? And indeed, we studied this system, once again changing the illumination angle, and we did observe the presence of these lattice resonances. This is we observe it for all the 3 lattice geometry, although probably the most evident one is this peak here around 850 nanometer for the L600 case, which moves very well according to theory when changing the incidence angle, as you can see here in this contour plot on the right. So just concluding my talk, I hope I convince you that this chemical pattern in situ growth system has incredible potential for a variety of different systems and targeting many different applications. And there is a lot of work to be done. Here I show you only gold nanoparticle on PDMS with only one chemical inking system. And I believe that by modulating both the chemical environment and the substrate physical-chemical properties, this will open up to a lot of research done in the direct preparation of plasmonic metasurfaces, where you have total control over the system chemistry, which can have very important implication for biosensing and optoelectronics, as well as electrophotocatalysis. So with that, I would like to conclude and thank the entire NanoOpto group at ICMAB, and specifically the 3 students that work with me on the data that I presented you today, and of course both collaborators and our fundings. And I'd like to thank you very much for you attending the talk, to Matt and the organizer for inviting me, and I'm really looking forward for the coming panel discussion.
All right, thank you, Leo. That was fantastic. Okay, so I think now we are at the point where we can initiate discussion. I thought maybe one just curiosity that came to mind that we can start discussing is, in a sense, kind of merging the 2 talks. Leo, you mentioned the idea of hot electrons, and I got thinking about, well, when you create this hybrid mode that is both photonic and plasmonic, I mean, how do I think about hot electron generation in a system like that, where the mode is now delocalized? Where can I still generate hot electrons in a delocalized mode? And if so, where do they, Dayne mentioned the importance of hot electrons appearing at certain undercoordinated sites. I don't know how to think about that when the mode is delocalized. Do either of you have thoughts on what that would look like, or if that's interesting, or maybe that's a bad question?
No, that's actually a great question. So there is actually a little bit, very few works in plasmonic driven catalysis looking at lattice modes. There are some appearing, like it's definitely something that people are starting to think about. The way I would look at it is that these are both plasmonic and photonics mode, but the way that you observe your lattice resonances is always basically an hybridization between your diffractive modes of the array and your localized plasmonic of the nanoparticle. So at the end of the day, there is always a plasmonic component, and so I think that by illuminating the lattice resonance, you still could create some hot electrons. Of course, the energies tends to be lower of the illumination, so that is definitely something to take into account. So I'm not sure. My guess that would be that the amount of odd electrons that you produce are definitely probably smaller. Though the idea is that you might have it compensated by the fact that they're still exciting the electrons, because those are plasmonic resonances anyway in a way, and those are much longer lived.
Your lifetime is orders of magnitude longer. So yeah, you may maybe lower energy, and so per unit, but per unit time, your yield, because your mode lives for so much longer. Even if per unit time your yield of hot electrons was lower, because it lives so long, you still might generate more hot electrons. I don't know.
Correct. That's the bet, at least.
That's the hope.
Yeah, and one thing that got people really excited about the in situ growth is that you can control the chemistry. So the problem that they have here is that they have performed some studies using traditional nanofabrications. Those are, of course, very, very good models, but the performance is not great. In terms of the chemistry of the system, so we need more control. I think that self-assembly is a possible approach, but the presence of ligands and all the correlated issue with that, it's a problem when you're trying to do catalysis. So, for example, in our case, we use PEG, and if once you have PEG on top, it's hard to control the chemistry there.
Well, you could imagine trying to rip the ligands off afterwards once you had made the structure that you wanted through plasma etching or something like that. Dayne, do you have thoughts on hot electrons from hybrid lattice plasma modes?
I think it's a really good question. I think it's something that's really important to think about. I don't know if I have a good answer for thinking about how you have the localized plasmon resonances in the individual particles and how the overall collective is going to behave. I mean, I feel like the collective effect wouldn't generate hot electrons across everything, but you do have these sustained, long-lived, high-quality factor resonances, which are really, really important. So I think I would kind of agree with Leo that even if they're lower energy and they're longer lived, there's still a lot of opportunities to utilize those for chemical transformations. Particularly, I had a slide about the importance of orbital overlap and hybridization with the metal that you're going to be using. So if you had a particular molecule that when it chemisorbs to a surface is going to create a resonance state, if you overlap the high quality factor resonance with, I don't know, the LUMO of some benzene derivative, I would think that you'd be able to selectively inject electron density into one bond or another based on that absorption geometry. And I think where these meta surfaces are really, really going to play a big role, and I think there'd be some really interesting future studies on, would be to, do a computational screening, figure out where your, I don't know, let's just say nitrobenzene is going to have its absorption energies on a gold nanoparticle surface, for example, and then tune your lattice resonance so that you're, let's say, like on the nitro group, and then off tune it to maybe like the carbon hydrogen bond, and see if you can steer a selectivity pathway that way. And I think, even if the overall surface area is low, the quality factor increase and the shorter, lower energy electrons, I would suspect would play a role there. But I think it brings together a lot of things all at once, but it's an interesting area that could have some cool future exploration in.
Yeah. One thing that you made me think about, Dayne, is that the one also very big opportunity might be realized by strong coupled system. So if you are able to have sufficiently good optical cavity, you should be able to really modify basically the chemical landscape of the molecule that you have absorbed by literally hybridizing their molecular orbital with the optical cavity, which I guess is an extremization of what we were talking about. And so in that case, you would have like you could literally directly pump the hot carrier directly into the molecule that you have absorbed. And so that
I think it'd be a way to get around some of the Fabry-Perot cavities that have seen similar strong coupling behaviors and steering chemical reactivities. It'd just be kind of an open-faced plasmonic cavity in a lot of ways. But I think that's kind of the other extreme of where other folks in the field are looking at. But it would be really exciting to consider more of.
Yeah, and I think that your inoperando system is definitely something that will be very, very cool to and I think you will be able to play around with this kind of microscopy and spectroscopy characterization, because in being able to see the system, how it behaves in real time is extremely important.
Yeah, agreed.
Okay, Matter, maybe I jump in for questions. Yeah,
Sure.
I'm working in microelectronics. Normally, fabrication technology is different, but yeah, I may have some questions is out of the chemistry, topics. So for Leo, I see in the last part of your talk, looks like, it's the uniformity is not very good. Yeah. So for the patterns, so any suggestion or any kind of causes?
Of course. I mean, yeah, the quality of our prepared arrays in the for the in situ growth part is definitely there's a lot of room for improvement. We are currently improving quite a lot compared to the images that I show you in the presentation. We are I guess the problem is a problem of optimization. So far we have explored literally a single substrate with a single system and a single chemistry, a chemical ink. And I think that's the limiting factor here. So the problem is to keep exploring. And I think there's a lot of room for improvement, but we are not out of ideas, let's say. One thing that get me more excited, actually, I mean, I show you here in basically on the spherical products, and I think that the opportunity here moving forward is trying to address nanostructure that you cannot prepare in solution normally. So trying to look for growth condition that could, the outcome would be something that you could not prepare by colloidal synthesis, and so that would definitely be a very big plus for the system. But yeah, you're definitely right. I mean, we are in the infant stage. The paper was published about a year ago, and yeah, there's definitely room for improvement, and we are looking forward moving on in that direction.
Okay, yeah. Another question, also in very related. You mentioned about the size, right? Yeah. Also, the kind of the structures now it looks like all the round one, right? Yeah. Did you try any other shapes?
That is a very good question. Yes, so we did not try optimize any other shape other than the gold nanostars that I show you right now. We are focusing on controlling the nucleation and having it be able to control the nucleation down to the nanoscale. Right now, as I mentioned, the area where we're growing is 230 nanometer. We are looking to bring it down to about 80 nanometer, and then trying to reduce the size of our nanoparticle as much as possible and trying to control their shape. That would be the next step. Since as Matt is definitely very aware of, it's very hard to grow something anisotropic when you start with a 20 nanometer nanoparticle. It's much easier if you manage to go down to, let's say, sub 10. Would be better to reach 5 nanometer. Which opens also to a whole another problem about characterization of the system, because we cannot use TEM, so we rely on SEM and other scanning technique, which are much harder to use on non-conductive substrate. But so apart from all these challenges, the idea would be to yes, we are thinking about targeting some anisotropic structure. One thing that makes me very positive about it is that if we observe, if you remember one of the slides where I showed the statistics, if you look at the few particles that were in that image, you could see some platelets and you can see some nanorods. And these are the typical, let's say, byproduct or structures that you would observe in a colloidal synthesis when you don't do it very well. So if you do a synthesis where you're not controlling the what you're producing too much, or just reducing gold, those are the typical products that you observe: some platelets, some nanorods, and some decahedra. And so the fact that we do observe the same type of products tells me that at least to some extent what we know from colloidal synthesis will be translatable to this type of in situ growth system. However, as I mentioned in the beginning of this panel, like what get me excited is to move a little bit further than what we can do in colloidal synthesis. It's like, okay, if I can produce nanotriangles, that's great. If I could produce nanorods, that's also great. But what I think is that we should use the physical-chemical properties of the substrate and the fact that my nanostructures are nucleating and growing anchored to the substrate, which basically takes away the whole problem of colloidal stability that we have in synthesis. Like in synthesis, we are limited in which type of chemical environment we can use, because we always have to ensure that our nanoparticles are stable during growth. And in this case, I wouldn't say forget about it, but let's say I could probably stretch the system a little bit more and force it a little bit further away and explore new synthetic condition because my nanostructures are chemically bound. And also strain on one side, like steric hindrance, of course, they will not be able to grow into the substrate. I guess that they will grow on the other direction. So those are the things that I think are more promising for this type of system.
Okay, super. Yeah, so Danny, Leonardo say hello to you. Yeah, he listened to your talk today, and it's say hello to you. Actually, I have a question for you. Is for what's exactly the dilute meaning? You have this kind of special word. So what's exactly it meaning?
So dilute, I guess, doesn't have an exact meaning as of yet. So there's the limit would be the single atom limit, where you have an individual, let's just say platinum atom that is isolated with a sea of gold or silver or copper atoms around it. That would be the very, very far extreme of this. But as I pointed out, there's a couple of papers at this point and several more that weren't included in my talk that have shown that you don't need to have a single atom isolated system to have a well-defined active site. And sometimes if you have a trimer of platinum atoms or even a smaller raft on the surface of your much larger nanoparticle, the reactivity will change and actually could be improved in that way. And so when I say a dilute alloy or a dilute plasmonic alloy, I'm really referencing a certain set of circumstances where you don't have a full atomic shell. I think, as soon as you have a full layer of platinum across your gold nanoparticle, in my opinion, that become a core shell feature. So I would think when you begin to shrink that shell down so it's patchy, that anything in that regime between single atom to patchy shell would be a dilute alloy in my opinion. I think that's really a region where we're going to have a lot of interesting chemical reactivity because of the isolated reactivity of some of these platinum sites or rhodium or whatever your favorite transition metal is. And I think that's going to be a interesting region to explore in coming years.
Okay, super. Also for the doping. Yeah, normally in microelectronics, we use a the doping process. It sounds like sometimes we use substrate is single crystal, sometimes it's poly, sometimes it's amorphous. So here, did you have any limitations?
No, at this point we don't have limitations because the most of these metals are miscible with each other. So you can make regimes between 0 and 100%. A lot of times, every once in a while, I think gold platinum is one of them. You can create an intermetallic phase where you get a really well ordered periodic array. But most of the time, unlike doping in semiconductor manufacturing and microelectronics, where you're looking at oxide materials, the metals behave really well together most of the time. Sometimes you'll get a Janus structure. I don't have an example off the top of my head, but that usually comes in a regime where you have a lot more of your dopant, kind of 25% or something like that, where you get phase segregation. At these low regimes, typically everything will mix together to some degree, or at least that's been my experience. Maybe Leo and Matt can comment on it as well if they've had anything pop out in their careers that's been different than that.
I think you've got it.
I think you've got it.
The lattice parameters are very, very different and you have a large, like you said, 25% or more, 25, 75, then they would rather phase separate than form very, very strained, one strained interface rather than many strained interfaces, so they'll phase separate. But you're right, most of the coinage metals are almost 100% miscible with each other. So yeah, that's not too hard to make alloys.
Mm-hmm. Yeah, exactly.
And in your case, you never. I mean, I think that your synthetic condition for the, let's say, for the alloying, or anyway for the dopant is not enough for have these dopant atom to migrate within the crystal. Like you're assuming that you always have them on the surface, correct?
We're not assuming that they're always on the surface. And actually, we know that, let's say, if we make gold platinum alloy, if we put it into a reducing environment like hydrogen, we can pull the platinum out, but if we put it into an oxidizing condition, you'll actually send it back down into the subsurface. And so I did make the comment during the talk, these are very, very dynamic processes. And so some of the in situ electron microscopy, hopefully like gas phase type cells with heating and laser illumination over the next couple of years are going to be able to give us some insights into those atomic migration patterns and how that all kind of plays a big part together. But yeah, the reaction environment matters a lot. Even in the case of carbon monoxide, I had that CO drift spectra that we showed the narrowing after we heated it up. And that suggests that carbon monoxide, because it binds so strongly with the platinum, can actually pull some of those atoms to the surface and then help them disperse across the larger area. So there's a lot of dynamic effects at play, which makes it tough, because for the last 10 years of my life or so, I'd make some nanoparticles and be like, cool, we got it. But now as we start to put these into these reactive environments, they begin to change in ways that there's some stuff that's known about, but I think there's a lot more to learn as well.
Certainly.
Do you have that much dynamics at room temperature that you can see migration of platinum from the center of the particle out to the surface, or is that more at elevated temperature?
Elevated temperatures, yeah. So
Yeah.
this would be like in a CO atmosphere at 400 degrees Celsius or something. They'll migrate out quite a bit. Yeah.
Okay. Yeah, I was going to ask, is there a role for ligand chemistry and coordination, selective coordination, to try and pull atoms towards the surface? But you just answered the question. You just said that it works with CO, so you can kind of control the radial distribution of the dopant through coordination with some other gas phase or molecule. That's really cool.
Yep.
Yeah. You can
also change crystal structure too.
Right? Yeah. And then you should also observe all that in the optical response, right?
Yeah, so you can, if you look at the plasmon resonance, you can see small shifts as you introduce, let's say, hydrogen. But I don't know how much of that is a restructuring effect or how much of that is a local dielectric type of effect between adsorbed gases overall on the surface. But yeah, you can see optical signature changes as you introduce different gaseous environments at different temperatures. Even the support, actually, because there's electronic interactions between the aluminum oxide and the metal nanoparticles that we support on. And so if you switch between silicon dioxide to titanium dioxide or cerium oxide, you'll get different optical responses from that as well. So there's a lot of complications in some of these metal nanoparticle catalytic type systems.
So for you mentioned, Dayne, this observation or this theoretical prediction that hot electrons would emit selectively from undercoordinated sites. That seems unintuitive to me. In some ways, it seems intuitive in other ways. I mean, how should I rationalize a collective oscillation? Localizing what is it that causes the localization at the undercoordinated site? And I guess that's kind of like an opportunity to engineer like tips of nanoparticles if you know more about what the geometric factor is that governs emission of hot electrons. If you could engineer the geometry of the tip correctly, you could try and have some kind of localized emission of hot electrons at a specific location. But how do I think about why that occurs selectively at an undercoordinated tip?
Right. Yeah. I mean, that's a really great question. I mean, to put everything into context, in terms of like a plasmon resonance, we typically think, I mean, Leo, how big were your particles? They were somewhere between like 20 and 50 nanometers or so, some smaller ones, some bigger ones. So like those particles, they've got tens of thousands or hundreds of thousands of atoms in the collective. And the example that I gave was really pushing towards like cluster chemistry, like 2 to 3 nanometers. Yeah, 561. And so it's really this atomistic simulation. And I think it's just that limit. So if you had a gold nanotriangle, a lot of people are familiar with the concept that as you have that triangle, the tip or the field enhancement localizes at the tip. And that's not an atomistic simulation, but those atoms that are very much right at the tip are going to experience the highest fields all the same. And so I think what this TDDFT study done by the Chalmers group showed is that as you shrink these nanoparticles down to sizes that are very catalytically relevant with undercoordinated sites, and you begin to look at this with an atomistic model, that you could actually think about carriers at the atomic scale. And then that second kind of follow-up paper that was published in May in the Journal of Physical Chemistry C, when you have a silver particle but you put in platinum, you can actually change the energetics and the localization of those carriers with the dopant site. And there's been other folks, not in the plasmonics community necessarily, that have looked at what happens if you put a copper atom into a silver nanoparticle. Again, 100% miscible, but if you push it down to that dilute limit or the single atom limit, the band structures actually don't mix together. So the copper atom sitting on the top surface will have free atom-like D states, which is something that'd be more akin to like an enzymatic center or a homogeneous catalyst than, you know, a pure metal phase. And so you kind of host these dopants in there, and kind of thinking about how that would change and influence any surface chemistry is pretty interesting. So yeah, I think, Matt, to answer your question, this is just from the simulation standpoint, taking what we already knew about collective oscillations and where they're going to localize themselves. It's not like they sit on that corner site for milliseconds. I think it's just on average, you're likely to find them at the corners and the edges, as we would think about normal larger plasmonic particles overall.
Yeah, I guess I'm almost getting to a more philosophical question for like, how do we go from the collective perspective to the atomistic, discrete perspective? For, you know, the collective perspective, as you said, is high local electromagnetic field, but then this atomistic perspective is yield of hot electrons at a specific atomic site. You know, it's not always, there should be obviously a continuum of understanding from one to the other. It's just in my head, I'm not sure if I have completely bridged those two regimes perfectly. It's just not totally intuitive to me. But that's, you know, maybe no one knows the answer to that question, or
maybe not yet, but hopefully we will soon.
Yeah.
Okay, Matter. I have a good news to share. Yeah, tonight we have a 21,000 audience online. We're proud of that.
Oh,
It's
great.
really, oh yeah, it is very exciting. Maybe, you know, I have a question. Last question is for Dayne. Yeah, I know that you will run for another talk. Yeah, today is a Halloween. So can you tell us something how you celebrate Halloween as a scientist?
Sure. So yeah, what Alice is saying, or kind of sharing, is that I have to go teach my general chemistry class. So, and I don't have 21,000 students, but I've got about 100 of them that are going to be waiting for me in 20 minutes or so. And so part of the Halloween celebration, I guess, is just to do spooky and scary things. And so part of my lecture today, we're going to explode a pumpkin. So we have it pre-carved, and we're going to put calcium carbide in water. It makes acetylene gas, and then we put a lighter in the back, and when we light it, it kind of blows the pumpkin apart. We've got carbon snake, which is the reaction of sulfuric acid and sugars. It just makes a big black kind of mass evolves out. And then we've got a demonstration called Goblet of Fire. So we light boric acid, and it creates a green flame. And so trying to teach chemistry in a more fun way than, you know, wave functions and overlap theory.
Okay, exciting. I think your students will love that. Now, 21,000 students here already hear that story. Yeah.
Happy to share about plasmons anytime.
We need to get to explode a pumpkin using plasma. That would be pretty cool.
Yeah,
Next time I'm on ICANX, I'll explode a pumpkin.
Sure, yeah. You have a lot of chance. Next year we're going to I have a one invitation for both of you. As you know, Matter was last year's winner for Young Scientist awards on ICANX. And now this year we are calling. Yeah, next week will be officially announced that calling for the Young Scientist candidates. Both of you are welcome, and we will celebrate the the Young Scientist awardees and Davos next year. So yeah, it will be a big fun. Yeah, just to take your fun chemistry there.
Sounds good.
Yeah.
Yeah, super. Yeah. No matter, I think we can,
Okay. Yeah, well, okay, thanks one last time to Dayne and Leo for two fantastic talks and teaching us about, you know, some very interesting new directions in metal nanoparticles and plasmonics. And thanks to Alice and ICANX for hosting this. And you know, I hope people got interested in this and checked out some of the research from these two great young scientists.
yes,
Yeah,
next
thanks.
week
Thanks for
we're
having
going
us.
to, yeah, next week we're going to have another group as well. We talk about brain interface, yeah, machine interface. So
Okay.
that will be another hot topic. So welcome everyone. Jump in next week at same time. Hey,
Okay, great.
Okay.
Thank you.
Thank you, everybody.
Bye.
Thank you, everyone. Thanks for having us.
Enjoy.
Bye-bye.
Enjoy Halloween.
Hi, everyone.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞越最高山岗。
祝你生日快乐！该吹蜡烛了，
来，我帮你。啊！
祝你生日快乐！
生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器。